Hello everyone, this is Jerry Huang from ETH Zurich. Today I will introduce our paper. Model-based RL for min-field games is not statistically harder than single-agent RL. This is a joint work with Niall and Andreas from ETH Zurich. We know that many real-world scenarios can be modeled as multi-agent systems. For example, the computer games, football games, or the electronic management systems. In those systems, each agent will take actions according to their current state and interact with the environment together. They will receive some rewards and transit to some next state, depending on the current state action of all the agents. In the multi-agent system, one interesting and popular objective is to learn the equilibrium policies. And the equilibrium policies basically means that if all the agents take that policy, no one can increase their return by deviating from the current policy. However, when the number of agents n is very large, we will suffer from the curse of multi-agency issue because the state space and also the complexity of the multi-agent system will grow exponentially with regard to the number of agents. And as a result, in general, in the large population scenario, the learning equilibrium can be intractable. However, in some scenarios, the problem has some special structures we can leverage, and this provides some opportunity to break the curse of multi-agency. For example, in some cases, the agents exhibit some symmetricity or interchangeability properties. Take the traffic system as an example. Here, we do not care about the particular state action of some particular agent, but only the state density matters. And we can model the reward and the dynamic of the system by some function which depends on the agent's current state action and the empirical state distribution of all the agents. And when the number of agents n is very large, we can apply the min-field approximation, and that will result in the well-known min-field games setting. The min-field games has various applications in finance, economics, and industry engineering. And this is the focus of our paper. And more formally speaking, in this paper, we consider the episodic or say the finite horizon min-field games. We use M to denote the min-field game model, which can be specified by a tuple with 6 elements. Here we use mu1 to denote the initial state distribution. S and A denote the state action space. H means the maximal horizon length. P and R denote the transitional reward function. We consider the case when all the agents take the same policy. So we only need to focus on representative agents because the agents are interchangeable. And for that agent, it will sample its initial state from the initial distribution. And at each time step, it will sample the action according to the policy and transit to the next state and receive some reward function. Here, the transition and reward function will depend on its current state action and also the expected state distribution induced by the policy pi, which we denoted as mu pi. And in the min-field game setting, we do not suffer the curse of multi-agency because here only the state density matters. The transition and reward function does not explicitly depend on the number of agents. And in this setting, we are interested in the Nash Equilibrium policy. To define the Nash Equilibrium, we first introduce a new notation, Jm pi tilde pi, which is defined to be the expected return of the representative agent. If it takes policy pi tilde, while all the other agents takes policy pi. And here the expectation over pi tilde and m pi is a short note of the expectation over trajectories sampled by the representative agent. And the Nash policy is defined to be the policy such that if all the agents take that policy, the representative agent does not have incentive to deviate because other policies cannot improve its policy value. And we can generalize to the notion of the epsilon approximate Nash, which basically introduce epsilon tolerance on the objective. And the key question we would like to address in this paper is the fundamental sample complexity of learning epsilon Nash equilibrium in MIFIL games with general function approximation. And next, let me discuss the motivation for this main objective. So first of all, usually the learner does not have the full knowledge about the mean field model, which means it needs to interact with the mean field system to do some exploration in order to learn the equilibrium policy. And the interaction, or say the sample collection in the mean field game system can be quite costly because it involves a large population of agents. And therefore, the sample complexity matters, and we need some efficient exploration strategy. And secondly, many real-world applications has rich observation and action spaces, and we need function approximation. For example, the neural networks to approximate the value function or the transition and reward functions. That's why we consider the general function approximation setting. And thirdly, the understanding of the sample efficiency of learning Nash equilibrium in function approximation setting in MIFIL games is quite limited. Although there are already a large number of papers study the function approximation setting in single agent RU or the Markov games, but the MIFIL games has some special structure, and the previous results cannot be easily generalized here. And next, let me formally introduce our basic setting. We consider the model-based function approximation and assume we can get access to a model class with finite cardinality. We will assume the knowledge of the reward function and only the transition function is unknown, which basically means for each model in this model class, it associates with the same known reward function, but different transition functions. And our results can be extended to the case when the reward function is unknown. We consider the following two standard assumptions for the model class. The first one is the realizability, which assumes the true unknown model denoted as M star is included in this model class. The second one is about the Lipschitz continuity, where we assume the transition and reward function is Lipschitz with regard to the density. And this is reasonable because the Nash equilibrium may not exist if this assumption does not hold. In the previous MIFIL game literatures, people usually consider the contractivity or monotonicity assumptions. The contractivity assumes that the Lipschitz coefficients are relatively small and some other additional assumptions. And monotonicity, in those papers regarding monotonicity assumptions, people usually assume the transition function is independent with regard to density and some other additional assumptions. So in general, comparing with assumptions in the previous literature, our assumptions is relatively weak. And next, let me show you our main results. So we establish a sample complexity for learning epsilon Nash in MIFIL games, which has only polynomial dependence on those key parameters. Here we use DMPE to denote the complexity of the model class, and which is a new notion called the Partial Model-Based Eluder Dimension, which we proposed in this paper. And it can be regarded as the complexity of the single agent model class converted from the original mean-field model class. We also provide some examples and show that this partial model-based Eluder dimension can be low in many cases. For example, in the tabular mean-field game setting, we can upper bound it by the number of states and actions, which basically implies the tabular mean-field game is sample efficient in general. And second example is a linear mean-field game, where the transition function can be decomposed to the product between the some linear or matrix features. And we can show the complexity will be upper bounded by the state action, by the dimension of the state action feature. And next, let me briefly explain the main idea of our algorithm design. So we propose a novel model elimination algorithm for the mean-field game setting. And in each step, we first choose some desired policy, denoted as pi k, and use pi k to convert the mean-field model class to a single agent model class by partially fixing the reward and transition function, the density in the reward and transition function. with density induced by the policy pi k in that model. And next, we will collect samples and eliminate those models disagree with the true model condition on that policy. And the third step is actually a single agent model elimination process because we already fixed the density in the transition reward function. And that is also the only step requires samples, which is a region of our dependence on that partial model-based Eluder dimension. And the key innovation in our algorithm is the design of the desired policy so that we can do the model elimination as efficient as possible. And next, I will use some visualization to illustrate the main idea of our algorithm design. So let's first consider an epsilon cover of the policy space. And for each policy, we can plot the single agent model in a figure. And here each dot denotes the single agent model converted from the original mean field model by fixing the density with the policy. And here the distance between two dots represents the model distance between two models. And we can do that for each policy, and it will result in a sequence of figures. And next, we can separately consider two cases. The first one is the non-concentrated case, which basically means there exists some policy, so that condition on that policy, there is no model cluster contains half of the models. Or in another word, all the models are scattered and far away from the others. And in that case, all we need to do is just choose that policy to be the desired policy package. And because after the elimination, we will throw out those models disagree with the true model. And because the models are kind of scattered, so we can eliminate half of the models in this model class. And the second case is more challenging, which is what we call the concentrated case. Basically, for every policy, there exists a cluster containing half of the models. And our key observation in this mean-field game setting is what we call the local alignment lemma, which basically means that if we find some model that aligns with the true model condition on its equilibrium policy, then that equilibrium policy would also be an approximate equilibrium policy of the true model. And under the Lipschitz continuity assumption and by some construction, which we omitted here, we can show that if we are currently under the case 2, there should exist some policy that policy would be an approximate Nash equilibrium policy of all the models in that cluster. And in that case, if we choose that policy to be the elimination policy package, then it will result in two cases. The first case is that after elimination, the cluster is still inside the model candidates class. And that means the true model should be inside this cluster. And by applying this local alignment lemma, we can conclude that this policy should be approximate Nash equilibrium, and we can directly return it. And the second case is that the cluster has been eliminated from the model candidate. Although we cannot conclude anything about which policy is the equilibrium policy, but we successfully eliminate half of the model class. And combining with the case 1, we can conclude that in each iteration, either we can directly return an approximate Nash policy, or we throw out half of the unqualified models. And this concludes our main results. As a summary, in this paper, we propose a new complexity measure called partial model-based Eluder dimension, and contribute a novel model elimination algorithm for the mean-field game setting. The key message in this paper is that under the realizability and Lipschitz conditions, the model-based RL for mean-field games is not statistically harder than single-agent RL. And there are also some interesting directions for the future work. The first one is whether it is possible to extend some of our techniques to the decentralized setting. And secondly, currently our algorithm is not computationally tractable. It would be interesting to improve the computational efficiency of our algorithm, or maybe design some empirical algorithms based on our theoretical insights. And thanks for listening. If you have more questions, we'll come to our poster session.